Alright, so this is about to be section 3.3. The section is titled Concavity and the Second Derivative Test. In the last section, we studied increasing and decreasing and the first derivative test. When we took a derivative and set it equal to 0 and plotted numbers on the number line to figure out where a graph was increasing and decreasing. We're going to do something similar in this section with the second derivative as opposed to the first derivative. And before I jump into the section, we have to know what it means for the graph of a function to be concave down and visually, I guess, what it means for the graph of a function to be concave up. Basically, a graph is concave down over any interval, I'll say, where water will fall off as opposed to puddle. I don't know if this is the best definition, but something that's kind of bent over like this or like that, those will be concave down because if water was falling on those, it would just fall off. And then if a region of a graph is concave up, provided water will puddle, I guess, or it'll catch water. So if I flip those graphs over like this or like that, these two regions are considered concave up as opposed to concave down, because theoretically, I guess in here water is going to cup and catch in those regions. It's kind of subtle when we see a graph to determine whether over a specific interval the graph is concave up or concave down. And I have a handful of examples that I tried to physically label where the graph changes concavity. Concavity is kind of the word for studying concave up and concave down intervals. And I'm just going to go through the first 18 problems. They don't require any calculus. They just want you to visually get used to seeing what concave up and concave down are. And like increasing and decreasing, we describe where a graph is concave up and concave down in terms of open intervals and using x coordinates and not y coordinates. I had to make the graphs fairly big. So for each of the problems between 1 and 18, we're supposed to find the intervals where the graph is concave up and concave down. And then we need to find an inflection point. An inflection point is a point where a graph changes from concave up or changes concavity. So it's a point, so it has both an x and a y coordinate where the graph changes concavity. And in most of the graphs between 1 and 18, if not all of the graphs, I have the inflection point labeled, and I don't label anything other than the inflection point. So if I was staring at problem 1, I might as well do it since it's here. This whole region of the graph, it's all kind of bent over downwards. This region up to the point 0,2 is supposed to be the portion of the graph where the graph is concave down. And then after the point 0,2, it starts being bent the other way, and it kind of flips over. And now it's going to catch water as opposed to water is going to run off. And right there is going to be the inflection point. So this region that I wrote in orange is supposed to be the region that the graph is concave up, and the region that I did in pink is supposed to be concave down. The more of these that we'll do, the easier it's going to be to see the answers to what region is concave up and what region is concave down. And in order to describe the regions, I'm going to put infinities on the edges of my x-axis and the x coordinate of the point where the graph changes concavity. So, and I'm going to create intervals. So this region of the graph, even though I don't see the graph all the way out to the left edge of the x-axis, we're going to say the graph is concave down. So when I go to answer question 1 for part A, I'll say the graph is concave down from the region in the interval negative infinity to 0. And then in the interval 0 to infinity, the graph was concave up. Because at x equals 0, the graph changes concavity from concave down to concave up, we call that point an inflection point. So this graph, the inflection point, is the point 0, 2. And there aren't different kinds of inflection points. Like in section 3.2, we had maximums and minimums in terms of when the graph changes directions. But when a graph changes concavity, it's just called an inflection point. There aren't multiple kinds of inflection points. So for each of the 18 problems now, I'm going to just figure out where the graph is concave up and concave down for part A, and where, if I have an inflection point, I'll label it in part B. So there's problems 2 and 3, and I'll just kind of trace on these. In this first region for number 2, my graph is concave down again. It's bent over, and then right at the point 0.5, instead of being bent down, it's kind of bent up, and that's the concave up region. So this is the down, and then it flips to up. And again, if I threw numbers on the x-axis to describe the intervals, I take a negative and positive infinity and put them at the edges of my axis, and where it changes concavity, the x coordinate of where it changes concavity also can put on my x-axis. This pink region for 2a is the region where the graph is concave down. And I would describe that as the interval from negative infinity to 0. And then the next region, which I'm going to describe as 0 to infinity, I'm going to say the graph is concave up. That's the end of 2a. To do 2b, any point on the graph where the graph changes concavity is an inflection point. That point in 0.5 where the graph changes from concave down to concave up is an inflection point. I'm going to label inflection point as IP because I don't want to keep writing inflection point. And I'll probably start abbreviating concave up and concave down as well, because it's kind of silly to write all that. So you should be able to do something similar for number 2, or 3 should I say. If you can't get number 3, when I do number 4, it's going to kind of let you do it because they're similar to each other. 3 is more like 4 than it is like 2 for that matter. Alright, so when I look at number 4, this first region up to the point 0.4, this is where the graph is concave up. And then it flips over and turns concave down. So when I go to answer this question, I'd throw a negative infinity on the far left edge of the right axis, a positive infinity on the far right edge, the x-coordinate of the inflection point on the x-axis. So those kind of draw out my intervals. You can kind of see the intervals there. And for 4a, the graph is concave up. Probably not the best abbreviation, but it's what I'm going to use. In the first interval from negative infinity to 0, and it's concave down in the next interval from 0 to infinity. And for 4b, the graph has an inflection point at the point 0.4. Your 5 again is probably more like my 6 than it is like the 4, but you might be able to do 5 without me showing you 6. But if you can't, I'll do 6 here in a second. So 6 is similar to your 5. This first region right here, from everything that I've traced, is considered concave up. It's kind of bent up. And then the graph flips over at that point 2.1 and changes to concave down. So the first region I drew in orange is the region that's concave up. The second region that I drew in pink is concave down. And again, if I put negative infinity and infinity at the edges of my axis and the x-coordinate of the inflection point on my axis, I could see the interval. There's the interval from negative infinity to 2, and then there's going to be an interval from 2 to infinity. And when I answer 6a, the graph in the first interval from negative infinity to 2, it's concave up. Notice I'm using all round parentheses for these. And in the second region from 2 to infinity, the graph is concave down. And for 6b, the point looks like it's 2, 1. I kind of covered it up a little bit. That point 2, 1 is my inflection point. An inflection point is any point where the graph changes concavity. It has both an x and the y coordinate. When I'm writing the intervals where a graph is concave up and concave down, I'm only writing the x coordinates. So R7 and 8 are a lot alike, and they're a little bit harder because they have changes a couple times concavity. I marked those 2 points out. Each one of those points is where the graph changes concavity. And so I'm going to write the first region that I'm drawing over the graph is concave down, and then I'll change my colors. And then it flips over to concave up where it's going to hold water, and then it's going to bend back. And after it bends back, it's going to be concave down again. So the 2 regions I drew in pink are the regions where the graph is concave down, because in those regions the water would just kind of fly off of them. But in that middle region, the graph is concave up. I'm going to put on my x-axis a negative infinity, a negative 1, a positive 1, and a positive infinity, and try to describe these colored regions as intervals. The first pink drawing that I drew, that's a concave down interval, and that's the interval from negative infinity to negative 1. So when I go to write an answer to 8a, just because the concave down interval comes first, I'm going to say the graph is concave down between negative infinity and negative 1. Notice I'm only using x coordinates. In the middle interval that I drew in orange, the graph was concave up, and I'm going to take those values of x and say the graph is concave up in the interval from negative 1 to 1. And then in the last interval that I drew, that's going to be the interval from 1 to infinity. It's concave down again. So I'm going to just put that after the other concave down interval with a union symbol between. And that was the interval from 1 to infinity. For 8b, I'm going to have 2 inflection points because any place on the graph, any point on the graph where the graph changes inflections, whether it's from down to up or up to down, are considered inflection points. So there's going to be 2 inflection points. Usually I don't put union symbols between those. I'm not sure. That almost seems inconsistent. Usually I put commas between if you have multiple points as opposed to unions between multiple intervals. So you should be able to give 7 a crack. Hopefully it's readable. These points are the points negative 1, negative 1. So that point right there, if you can't read it, that's the point negative 1, negative 1. And this point, if you can't read it, is the point 1, negative 1. So you need to know the coordinates of those points to be able to answer the questions. And then your graph is similar enough to mine where you should be able to hopefully figure out the concavity. I'll show number 9 up here for you to do. And so, again, you need to be able to see these points. That point I think is pretty easy to see. It's the point 1, negative 5. This point might not be as clear to see. That's the point 3, negative 5. So you'll need both those points to get your concave ups and concaves downs. For 10 and 11, I labeled a point just because it's a vertex of a parabola, and I generally label those anyways. But that point's not an inflection point, because in problem 10, to the left of that vertex and to the right of that vertex, the graph is cupped upwards both ways. It's concave up everywhere. And at the point 3, 1, it doesn't change concavity. It's concave up over here. It's actually concave up and decreasing. Here it's concave up and increasing. But this graph is concave up everywhere. It's never ever concave down. So when I go to answer 10a, I'd put a negative infinity on the left edge of my number line, positive infinity on the right edge of my number line. There's nothing to go between it because it doesn't change concavity at all. So when I answer 10a, I would say it's concave up from negative infinity to positive infinity. And for concave down, it would be never. And for 10b, for inflection points, that 0.31 is not an inflection point because it doesn't change from concave up to concave down, nor does it change from concave down to concave up. So this graph has no concave down intervals. If you don't have any concave down intervals, you can't get an inflection point because you need to change concavity for that. So your problem 11, again, I hope that these points are readable. That's the point 4, -3 that I've marked out. That point's not going to be necessary in the answer, but I want you to be able to read it anyways. So 12 and 13 are similar to our last problems. When I look at problem 12, this region, it's concave down and increasing, and then at the vertex 4, 5, it's concave down and decreasing, but both halves of this graph on either side of the vertex are concave down. It's concave down everywhere. And so I wouldn't have to put anything on the x-axis other than the negative and the positive infinity. And when I go to answer 12 part A, I'd say for concave up, it's never concave up. For concave down, it's concave down from negative to positive infinity. And because it doesn't change concavity, when I go to do 12b, for inflection point, there won't be an inflection point. So 13 should be the same. Again, if you need this point, you don't really need this point in the answer, but it's the vertex is 1, 7, just in case it's not showing up as well as I'd like it to show up. All right, just a few more of these, and then we'll get into some calculus. So for 14, there's a vertical asymptote drawn through x equal to 2, and the graph is broken into two halves. The first half of this graph, the graph is concave down in that entire part because it's bent over. So this is going to be the region where the graph is concave down. The other half of the graph, it's concave up. And when you have asymptotes and you're trying to determine the intervals for concavity, you put the x-coordinate of the asymptote on the number line. So I'm going to put negative infinity and positive infinity at the edges of my number lines, and I'm going to include the x-coordinate of the asymptote to describe my regions for this graph. This first region, from negative infinity to 2, the graph is concave down. So when I go to do 14a, I'm going to say the graph is concave down between negative infinity and positive 2. The next half of the graph, it's all concave up, and that's the region from 2 to infinity. So the graph is changing from concave down to concave up. So there should be an inflection point, but because 2 is not in the domain of the function, there's no point on the graph that has 2 as its x-coordinate. There isn't an inflection point, because an inflection point has to be a point on the graph where the graph changes concavity. So even though the graph changes concavity at x equal to 2 from concave down to concave up, there's no point on the graph, because it's not continuous there, that has an x-coordinate of 2. So there is no inflection point, even though the graph changes concavity. Where the graph, the x-coordinate of where the graph changes concavity would have to be a point on the graph for it to be an inflection point. And an asymptote, a place that's not in the domain of a function, will never be a inflection point. So your problem 14 is similar. There's a vertical asymptote drawn at x equal to -3, and you have two halves just like I have two halves on my graph. One half is concave up, the other half is concave down. And similarly, even though the graph changes concavity, there's not going to be an inflection point, because where the x-coordinate of where it changes concavity, the graph doesn't exist. And the graph has to exist in order, actually it has to be continuous through that point to get an inflection point. Your 17 is more like my 18, so I don't know if you could jump into that yet or not. My 16 has a vertical asymptote drawn at x equal to -3. I'm also going to need the infinities on my axis. And there's two halves again. The first half of my graph, before the vertical asymptote, the graph is concave down. The second half of my graph, after the vertical asymptote, the graph is concave up. So when I go to answer 16a, I'm going to say in this region right here, between negative infinity and negative 3, the graph is concave down. And the next half of the graph is concave up between negative 3 and infinity. And for 16b, again, the graph changes concavity at x equals negative 3, but there's no graph there, there's an asymptote there. So for inflection point, there's going to be none. For your problem 17, there's a vertical asymptote at x equal negative 3. There's a point marked at 0, 0, and there's a vertical asymptote at x equals positive 3. And I'm going to go do problem 18. If you can't do problem 17, when I do problem 18, you should be able to do problem 17. So for problem 18, there's a vertical asymptote at negative 4. There's a point marked at 0, 0. And there's a vertical asymptote at positive 4. A lot like your problem 17. So this first region between negative infinity and the vertical asymptote, the graph is concave down. So as I go to write my answer, the first thing that I might do in part 18a is describe this region right here. In this region, the graph is concave down, and that's the interval from negative infinity to negative 4. And then I'm going to jump the vertical asymptote and get to the next portion of the graph. This portion of the graph, between the vertical asymptote and the point that I marked, the graph is concave up. It's kind of bent up as opposed to bent down. So I'm going to say the graph is concave up between x equal negative 4 and the x coordinate of that point, which is 0. After that point, the graph bends over again and changes concavity. And between this point that has an x coordinate of 0 and that vertical asymptote which has an x coordinate of 4, the graph is concave down again. That's going to be my interval from 0 to 4. Then we get a vertical asymptote, and the graph on the opposite side of the vertical asymptote was concave up again. That's from x equal to 4 all the way to the right edge of the x-axis, which is x equal infinity. So this, I'm going to describe that interval as 4 to infinity, and the graph is concave up in that interval. When I go to do 18b, the graph changes concavity 3 times. Here it changes from down to up, there it changes from up to down, and here it changes from down to up. The only time I'm going to get an inflection point is where it changes concavity at a point on the graph. So this point 0, 0 is going to be an inflection point. There isn't an inflection point at x equal to negative 4. There isn't an inflection point at x equal positive 4. So the only inflection point for this is at the point 0, 0. So you should now be able to do, maybe give 17 a crack. It's just like the one that I did. So I'll pause this video, and then I'll do the rest in a part 2, the calculus part. So this was all the freebie part, just getting used to what concavity looks like on a graph.